Hello, everyone. Today, building on the projection of a point, we formally begin the core topic, the projection of a line. A line is composed of infinitely many points. Its projection is essentially a collection of point projections. Therefore, the previous lesson provides an important foundation for today. To help you clearly follow the learning sequence, this lesson is still organized into 4 parts. First, a review of previous knowledge. We recall the key content from the previous lesson. Second, we clarify the learning focus of this lesson. Third, we explain the new knowledge points one by one. Fourth, we summarize and consolidate to improve understanding. Now, let us start with part 1, knowledge review. In the previous lesson, we focused on the projection of a point, and the key ideas can be summarized into 3 aspects. Let us recall them together. First, the projection rules of a point. The core can be summarized in 2 statements. Projection connecting lines are perpendicular to the corresponding axis. For example, a primer is perpendicular to the z-axis. A double prime is perpendicular to the z-axis. The distance from the projection to the axis equals the distance from the point to the plane. For instance, the distance from A to the x-axis equals the distance from point A to the v-plane. This is the fundamental basis for drawing and reading engineering drawings. Second, the relationship between the projection of a point and the right-angle coordinate system. Each projection contains 2 coordinate values. For example, the horizontal projection A is expressed as x, y. The frontal projection A' is expressed as x, z. Therefore, 2 projections of a point contain all 3 coordinates. Thus, its spatial position can be uniquely determined. You must remember this conclusion clearly. Third, the relative position of 2 points and coincident points. To determine the left, right, front, back, and up-down relationships of 2 points, the key is to compare the coordinate values. A larger x value means the point is on the left. A larger y value means the point is in front. A larger z value means the point is above. Coincident points refer to the special case where 2 points coincide in projection on a projection plane. When determining visibility, the hidden projection should be enclosed in parentheses. For example, for coincident points on the h-plane, visibility is determined by the z-coordinate. The projection with the larger z value is visible. After reviewing what we learned last time, let us clarify the core content of this lesson. These are the key objectives for today. First, construction of a line's 3-view projections. Second, projection properties of lines in different positions. This is the key focus of today's lesson. Third, points on a line, projection rules and applications. With these objectives in mind, we now begin the new lesson. First, 3-view projections of a line. Let us first consider, how do we obtain the projections of a line in space? Based on what we learned about point projection last time, it is easy to see that a line is determined by its 2 endpoints. Therefore, its projections depend on the projections of its endpoints. In terms of projection properties, in general, the projection of a line is still a line. There is only one special case. When a line is perpendicular to a projection plane, its projection concentrates into a single point. This will be important later. Based on this, the method for obtaining the 3-view projections of a line is clear. First, draw the 3-view projections of the 2 endpoints of the line. Then, on each projection plane, locate the endpoint projections, that is, the projections on the same plane, and connect them with straight lines. In this way, you can obtain the 3-view projections of the line. For example, line AB. First, draw a double prime for point A and B double prime for point B. Then connect AB, a prime B prime, and a double prime B double prime. These 3 connecting lines are the projections of line AB in the 3 views. This method is very basic. You must practice it yourself to master it. Second, projection properties of lines in various positions. For a spatial line in the 3-plane projection system, according to its relative position to the projection planes, it can be classified into 3 types: lines parallel to a projection plane, perpendicular lines, and general position lines. The projection properties of these 3 types differ significantly. They are also key points for subsequent drawing and interpreting drawings. We will go through them one by one. First, lines parallel to a projection plane. First, the definition. A line parallel to one of the primary projection planes, and inclined with respect to the other 2 primary projection planes. is called a projection plane parallel line. Since there are 3 projection planes, it can be further divided into 3 types. A frontal line, parallel to the V-plane, a horizontal line, parallel to the H-plane, a profile line, parallel to the W-plane. We will use specific examples to analyze their projection properties one by one. Please observe with the figures on the slides. First, horizontal line, parallel to the H-plane and inclined to the V and W planes. Take horizontal line AB as an example. Its projections have 3 key features. First, the horizontal projection AB is equal in length to line AB in space. That is, it shows the true length. Second, the frontal projection A'B' is parallel to the x-axis. And the profile projection A'B' is parallel to the YW axis. Neither of these projections shows the true length. Third, the angle beta between the horizontal projection AB and the x-axis is equal to the inclination angle of AB to the V-plane. And the angle gamma between AB and the YH axis is equal to the angle of inclination of AB to the W-plane. Second, frontal line, parallel to the V-plane and inclined to the H and W planes. Now consider frontal line CD. Its characteristics are, first, the frontal projection C'D' equals CD, showing the true length. Second, the horizontal projection CD is parallel to the x-axis, and the profile projection C'D' is parallel to the z-axis. Neither shows the true length. Third, the angle alpha between the frontal projection C'D' and the x-axis equals the angle of inclination of CD to the H-plane. And the angle gamma between C'D' and the z-axis, equal to the inclination of CD to the W-plane, are shown in true magnitude. Third, profile line, parallel to the W-plane and inclined to the V and H planes. Finally, let us consider profile line EF. We observe that, first, the profile projection E'F' equals EF and shows the true length. Second, the horizontal projection EF is parallel to the YH axis, and the frontal projection E'F' is parallel to the Z-axis. Neither shows the true length. Third, the side projection E'F' and the angle alpha with the YW axis, the inclination of EF to the H-plane and the angle beta with the Z-axis, the inclination of EF to the V-plane represent the actual angles. Let us summarize. These 3 types of lines parallel to a projection plane share common projection properties. You can remember them with 3 key points. First, on the projection plane to which the line is parallel, the projection shows the true length. Second, on the other 2 projection planes, the projections are parallel to the corresponding projection axes and do not show the true length. Third, the angle between the projection showing the true length and the projection axis equals the angle of inclination of the spatial line to the corresponding projection plane. If you grasp these common features, you will not get confused. Second, lines perpendicular to a projection plane. Next is the second type, lines perpendicular to a projection plane. They are defined as lines perpendicular to one principal projection plane. Since the projection planes are mutually perpendicular, such a line must be parallel to the other 2 projection planes. Similarly, there are 3 types: the frontal perpendicular line, perpendicular to the V-plane, the vertical line, perpendicular to the H-plane, and the profile perpendicular line, perpendicular to the W-plane. We will again analyze them using examples. First, vertical line. It is perpendicular to the H-plane and parallel to the V and W planes. Take vertical line AB as an example. Its projection properties are very clear. First, the horizontal projection concentrates into a single point, namely A, B. This is called the concentrating property. Second, both the frontal projection A'B' and the profile projection A'B' equal the true length of AB. Moreover, A'B' is perpendicular to the x-axis, and A'B' is perpendicular to the YW axis. Second, frontal perpendicular line perpendicular to the V-plane, and parallel to the H and W planes. Now consider frontal perpendicular line CD. Its characteristics are, first, the frontal projection concentrates into a single point, C'D'. Second, the horizontal projection CD and the profile projection C'D', both equal the true length of CD. In addition, CD is perpendicular to the x-axis, and C'D' is perpendicular to the z-axis. Third, profile perpendicular line perpendicular to the W plane. It is parallel to the V and H planes. Finally, consider side vertical line EF. We observe that, first, the profile projection concentrates into a single point, E double prime, F double prime. Second, the horizontal projection EF and the frontal projection E prime F prime both equal the true length of EF. Moreover, EF is perpendicular to the YH axis, and E prime F prime is perpendicular to the Z axis. Similarly, lines perpendicular to a projection plane have three key characteristics. First, on the projection plane to which the line is perpendicular, the projection concentrates into a single point. This is the most essential identifying feature. Second, on the other two projection planes, the projections both show the true length of the line. Third, these two projections showing true length are each perpendicular to the corresponding projection axes. Compared with lines parallel to a projection plane, the concentrating property is the main distinguishing feature of perpendicular lines. This is important and must be remembered. Third, general position lines. The last type is the general position line. The definition is straightforward. It is a line inclined to all three basic projection planes. It is neither parallel nor perpendicular to any projection plane. Therefore, its projection properties are relatively simple. All three projections are inclined to the projection axis. None of the projections shows the true length of the line, nor can they directly show the angle of inclination to a projection plane. Although it appears ordinary, it is the most common type of line in engineering drawings. Let us consolidate the content with an example. Analyze the relative positions of edges SA, somebody, and AC of a regular triangular pyramid with respect to the projection planes. Please refer to the projection drawings on the slides, and follow the analysis step by step. First, consider edge SA. Its three view projections are S' a prime, SA, and S double prime a double prime. They are neither parallel to any projection axis, nor perpendicular to the projection axes. This matches the characteristics of a general position line. Therefore, SA is a general position line. Next, consider edge SB. The frontal projection SB is parallel to the Z axis, and the horizontal projection, somebody, is parallel to the YH axis. This matches the projection properties of a profile line we discussed earlier. It is parallel to the W plane, so its projections are parallel to the Z and YH axes. Therefore, SB is a profile line. Finally, consider edge AC. The frontal projection AC is perpendicular to the Z axis, and the horizontal projection AC is perpendicular to the YH axis. Moreover, the profile projection A double prime C double prime concentrates into a single point. This matches the characteristics of a profile perpendicular line, perpendicular to the W plane with the projection concentrated on the W plane. Therefore, AC is a line perpendicular to the W plane. From this example, you can see that, when determining the position of a line, as long as you compare the core projection properties of the three types of lines, you can reach a conclusion quickly and accurately. Third, points on a line. Next, we study an important incidence relation, a point lying on a line. Here is a key theorem. You must remember this: if a point lies on a line, then the projections of this point must lie on the corresponding projections of the line. Conversely, if the point's projections lie on the corresponding projections of the line, and they satisfy the projection rules of a point, then the point must lie on the line. In short, if a point lies on a line, its projections must lie on the line's corresponding projections. If any projection of the point does not lie on the corresponding projection of the line, you can conclude that the point is not on the line. Application example: constructing the projections of a point on a line. We apply this theorem using an example. Given that point M is on line AB, and it is known that the frontal projection of M is M', the task is to determine its horizontal projection M and profile projection M double prime. Based on this theorem, the steps are straightforward. Step 1. First, construct the complete three-view projections of line AB, especially the horizontal projection AB and the profile projection A double prime B double prime. Step 2. Through M', draw projection lines perpendicular to the x-axis and z-axis. Let them intersect AB and A'B', respectively. Hence, obtain M and M double prime. That completes the construction. The key is, a point's projections must lie on the corresponding projections of the line. Fourth, summary. That's all for today's lesson. Let us review the key points of this lesson. Please sketch the outline in your notebook. First, 3 view projections of a line. Core method is project the endpoints first. Then connect the corresponding projections. For a perpendicular line, one view degenerates to a point. Second, projection properties of the 3 types of lines. This is the key focus today. Please refer to the table below and use the slides to tell them apart. Lines parallel to a projection plane. First, true length. Second, parallel projections, and the inclination is shown as a true angle. Lines perpendicular to a projection plane. First, concentrated projection. Second, true length views, each perpendicular to its corresponding projection axis. General position lines. Third, all projections are inclined, showing neither true length nor true angles of inclination. Third, points on a line. The core concept is the projection incidence relation. Using this relationship, you can construct the projections of a point, or test whether it lies on the line. To help you consolidate today's content, here is one exercise. Please complete it independently after class. Use proper drafting conventions. We'll go over it in the next class. And I'll answer your questions. Finally, a brief preview. In the next lesson, Building on Line Projection, we will move on to projection of planes. We will explore the positional relationships between a plane and the principal projection planes, and the projection rules. This will lay the foundation for projecting more complex solids. That is all for today's class. Thank you. See you next time.